Hello, guys and gals. This is me, Mudahar. It's not Mudahar. I'm just joking, dude. I'm not even Indian. Okay. Let's do this. Edit video details. Edit. Video details being edited. Video details being edited. Tags. We are going to make tags. Copy and paste live stream tags that apparently get you views but are not working for me. Wah, 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 wah. Wah, wah. Okay. That's the tag set. Let's close that. All right. What's up, guys? Full cam this right now. What's going on? Okay. Today, what are we doing? Well, today we are going to be studying. Yes. 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 Sorry, things in my brain are going a little bit wacky, a little bit wacky. But what are we doing? Well, I'll tell you what we're doing, okay? Did I even say it? I don't even remember if I said it or not. Anyway, what we're doing is we are gonna watch a bunch of quantum mechanics lectures so that we can actually understand the info. I think there's only like what? How many videos can we even watch until the variational method? So there's 3 videos. Oh no, there's a lot. 1, 2, 3, 4, 5. So there's 5 videos up until the variational method. Let me double check with the syllabus. Yeah, fine structure of hydrogen, the Zeeman effect, variational method, WKB approximation. Yeah, WKB approximation, this lecture does not cover until very later. So I have a feeling his covering of it is probably going to be a lot more complicated because it's being covered near the end. But that's just an assumption. Don't know if that's true. But anyway, so put it back to normal, okay? And basically, what we're going to be doing is this. So we're just going to watch this. At 2 times speed.
With a bunch of states that are known. And here I'm drawing the states. But then there might be some degenerate states too. These states are degenerate.
Okay.
These ones are not degenerate. Just so where this is.
I can full screen this probably
and
too.
So the idea is that if I turn on a perturbation, then the question is, what are the new states? What do the new states look like? We want to solve this problem, H psi n equals En psi n, and we want to know what are these things. And of course, this is what we want, and this is what we know. We know that H naught psi n naught is equal to En naught psi n naught. And so we want to know what these new levels are and states for the perturbation. And the idea is that the perturbation causes me to be able to match up every known state, can go up to every unknown state as we turn on the perturbation. So this is the picture I want you to have in your mind. And then here I have 3 degenerate states, and these might split in some funky way by the perturbation, but these non-degenerate states just very nicely evolve into these new perturbed states. So these are the unperturbed states, and these are the perturbed states. And this line means here that we turn on the perturbation. And I just want you to keep that picture in your mind. Perturbed states. Okay, and so we know what to do in this picture. Then we know that to find the things that we want is the energy of the perturbed state and the perturbed eigenstate itself. And so to find those things, we use the perturbation expansion. And from the perturbation expansion, we got these beautiful results that we all know and love, which is that the new eigenstate, the perturbed eigenenergy, is the old eigenenergy plus a first order correction. And you can also have a second order correction.
Yep.
There's more, but we will ignore.
And the first order correction.
And then, of course, for the eigenstate,
it's the inner product.
We start with the unperturbed eigenstate, but then there are corrections. There's the first order correction, and then there's the higher order corrections, which we will ignore. And then I will just write one of these formulas. We know that, for example, psi n1 is equal to the sum over all m not equal to n over all the unperturbed eigenstates, psi m naught, h prime, psi n naught, all over e n naught minus e m naught, psi m naught. Okay, and then similarly, there's other formulas for en1 and for en2. I'll just write the one for en1 is the easy one, psi n naught, h prime, psi n naught. And then there's also a formula for en2. Okay, so this is our perturbation expansion, and this is the answer. All right. So that's why we like perturbation theory so much. It gives us a very simple answer. It tells us the perturbed. It gives us what we want, which are these two things right here. We get them. Yay! So happy. But of course, not all is perfect in paradise. So what we see then is that so the idea then is if someone gives you a Hamiltonian, which can be written as a part that you know plus a smaller part that you don't know, then and they ask you to solve it, then what you can do is you can say, great, use perturbation theory. And so if you want to find, for example, the nth eigenenergy, and if someone says, tell me all the allowed energies, then the first question you should ask yourself, if you're looking at some particular state, the nth state, then you have to ask, you want to use the perturbation theory expansion, but you have to ask yourself a question. What is the first question that you ask yourself? So I've given you a strange Hamiltonian, H prime, and I'm asking you, what are the allowed energies? I'm basically asking, tell me the eigenenergy of this new Hamiltonian. And you already know from your class that you should use perturbation theory because I'm giving you some weird Hamiltonian you've never seen before, some perturbation H prime.
Is it degenerate or non-degenerate?
Perturbation theory, and then I'm telling you, tell me, find me that nth eigenenergy. What's the first question you have to ask yourself?
Is the unperturbed state degenerate?
Yes, perfect. That's the first question.
Yep.
That's exactly right. Is psi sub n naught degenerate?
I got it, dude.
So,
I don't even have to be watching this, man.
If it's not,
I'm just
then what do
that
you get?
good.
Just plug it into those equations.
Yes. Then plug it in. And it's
Yep.
easy, or relatively easy. You know what to do. You just plug into the formula. But what if it's yes? What if it is degenerate? Then you have to ask yourself a new question. So suppose it is degenerate. Suppose that it turns out that there are multiple states of that energy. Suppose you're here.
Are the off to that
degenerate
diagonal
right here.
matrix elements of our new
So
Hamiltonian
then what question do you have to ask yourself
0?
to proceed? In order to go forward, what do you have to do? You have to ask a question. You have to figure something out. What do you have to figure out?
What the right eigenstates are for the degenerate subspace?
Yeah, but you might have them. You might already have the right states. How can you tell?
Is the matrix element equal to 0?
Yes, exactly. Which matrix element?
Of the Hamiltonian?
Off diagonal matrix element of what operator?
H prime
In what basis?
in the degenerate basis.
That's right, the unperturbed degenerate subspace. That's exactly right. Because the whole point is that you got to make sure that this formula right here, I'll circle it, that formula is going to blow up. And that formula blows up right here because if the two states have the same.
So if it is degenerate, then you check if the H prime, if our Hamiltonian in the degenerate subspace has off diagonal elements equal to 0. Basically, you check whether or not our H prime is diagonal in the non-degenerate subspace, so in that basis. If it is diagonal, then you're good. If it's not diagonal, then you find a basis to which to diagonalize it, and then you're good.
Same energy, this formula blows up. The denominator goes to 0. So you got to make sure that the numerator goes to 0.
Genius at perturbation theory. I'm a genius at perturbation theory.
Because
Okay.
the denominator always goes to 0 for the degenerate state. You got to make sure the numerator goes to 0, or else the perturbation expansion doesn't work. So
Yep.
if yes, then you got to make sure, you have to ask yourself, is the off diagonal matrix element of H prime equal to 0? Oops. Equal to 0, question mark. In other words, I can write it like this. Psi m naught H prime
Psi n naught
equals 0
question mark.
in the degenerate subspace.
I'm predicting what he's gonna
And what is the
say.
degenerate subspace? It just means the degenerate subspace just means that E n naught and E m naught are equal. That's what a degenerate subspace is. It just means the states that have the same energy. And so sometimes when people use this formula, by the way, shorthand, I write it like this. Okay, this is just a shorthand way of writing it. I just want you to get used to this notation. Because nobody wants to write psi m naught. It's so tedious. I would just write m, and it's understood that that's the unperturbed basis. Just want to get you used to that. So these are the off-diagonal matrix elements. So then, suppose that these off-diagonal matrix elements do equal 0, then what? Then what do you do?
Then we can just use the non-degenerate perturbation theory.
Exactly. Just
Yeah.
plug in.
Then you're good.
Plug into formulas. Easy, or relatively easy. I mean, it can be hard, but not that hard. But what if the off-diagonal matrix element does not equal 0?
I already know. You gotta diagonalize it. You gotta
What
find
do you do?
a basis to which to diagonalize it.
Diagonalize it, find the eigenvalues and eigenstate.
Exactly. But we can't diagonalize everything because that's the whole point of perturbation theory is to not diagonalize everything. Because if you diagonalize everything, then you're not using perturbation theory. That means you're just solving the Schrödinger equation. You see what I'm saying? So we want to do an easier problem. So we have to diagonalize what operator?
H prime.
We diagonalize H prime, but we diagonalize its restriction to the degenerate subspace.
Yes. That's it exactly. And that's important. Diagonalize H prime in the degenerate subspace. And the reason that's
Yes.
important is because that's not so hard. That's a much easier problem than diagonalizing H prime in the whole over the whole basis. Diagonalizing H prime over the whole basis is equivalent to solving the Schrodinger equation. And that's what we're trying to avoid because that's too hard. But diagonalizing H prime in the restricted subspace is much easier because because if when you're diagonalizing a matrix, if it's a small matrix, that's easy. If it's a big matrix, that's hard. So you're always trying to diagonalize a smaller matrix. That's what it always boils down to.
Because
Okay,
the degenerate subspace
but
is
you
only
could
like
diagonalize-
n dimensions.
You could
where
diagonalize H.
it's
So basically, you
probably
have to
going
diagonalize
to
H
be
prime in
like
the degenerate subspace.
3
But there's many ways of doing that.
or
There's
2.
many ways. How do you do this? One way is just brute force.
Yep.
You construct H prime matrix, and you diagonalize it like you learned in your linear algebra class. Then you diagonalize it with all those matrices and determinants and equations and stuff. It's a bunch of work. But another trick is you could just find a new basis that already has diagonalized H prime. That already diagonalizes H prime. So it turns out that the basis that you're using might not diagonalize H prime, but it turns out you have many choices of bases. And you might be able to find a new basis that does. And so this is something that we will be discussing more in this class, but I don't want to talk about it right now. But that's the perturbation strategy. So we just gone over the whole thing, perturbation strategy. That's the whole perturbation strategy. Okay, now it's time to apply the strategy to some different problems. Okay, so now this part of the course, we're going to apply this strategy to a few different problems. And the problems that we're going to apply it to is what we call the fine structure of hydrogen. We're going to apply this strategy to the fine structure of hydrogen. And you guys already have a little bit of introduction to that in the homework where you already were sort of looking at the relativistic correction. And so let's just discuss the fine structure of hydrogen quickly, or I mean, let's introduce it quickly. It's actually a fairly big topic, but let's talk about this. So what is the fine structure of hydrogen? Okay, so hydrogen is something that you know. I will sort of review hydrogen for you. Hydrogen is something that you know. It's basically atomic. It's atomic physics in a nutshell. I mean, all of atomic physics is sort of explained by hydrogen. That's why we love hydrogen so much. It's the simplest atom. And so hydrogen, of course, we all know we have a nucleus and we have an electron. And the electron orbits the nucleus, right? And it's sitting inside of a Coulomb potential. V goes as 1 over r. The Coulomb potential. That's when I draw these lines. That's the Coulomb potential. 1 over r potential. Okay, and so you've been introduced to this, and so you know then that the Hamiltonian of this problem is kinetic energy plus potential energy. And we always start with classical. Hamiltonians. I want to emphasize Hamiltonians are classical. So when we do quantum mechanics, we always start with classical mechanics, right? So we have our p squared over 2m, and we have our 1 over r potential. But then what we do in quantum mechanics is we turn them into operators, as you know. And so when we turn it into operators, then the kinetic energy becomes negative h squared over 2m. You guys will all know, plus, and then of course the 1 over r is negative e squared over 4 pi epsilon naught r. Okay, so that's our famous Hamiltonian. And then you guys solved that. H naught psi equals E psi. You solved it last semester, and you know that psi, you know that the psi, the eigenstate, so then you know that the eigenstate looks like this. The eigenstates of hydrogen look like this. Psi n l m of r is equal to, and there's a radial component, and then there's a spherical component, theta phi. Right, and so you guys know that these are the horrible Laguerre polynomials that nobody likes. And then these are the spherical harmonics, which everybody likes. Spherical harmonics are great. They are fun and good. We love them, but those Laguerre polynomials, nobody likes those. And then we know also that the energy is just going to be negative 13.6 eV over n squared, right? Okay, and so that's sort of the situation. And so then what we can do is, but the point is, and we can always add spin. We can always add spin. Just multiply. We can have psi NLM times a spin state, and so the spin state could be up or down. Okay, so we can always add spin as well. But the point, so this you guys know. So this you know all this from last semester. No, so this is our H naught and our psi N naught. This is the known stuff, the unperturbed states. But it turns out that there are other terms in the Hamiltonian, and I'm talking classical physics, in the classical Hamiltonian, that we ignored. What are they? Can somebody tell me? We ignored a bunch of terms in the energy Hamiltonian. Can anybody tell me what they are?
The interparticle interactions.
The what interactions?
The interparticle interactions in hydrogen in between the nucleus and the electron.
Well, we did already. The Coulomb potential is between those. So.
Oh yeah, sorry.
But you are right. Actually, there is another interaction between the electron and the nucleus that we ignored. So you are right. But do you know what it's called?
Is it the
spin
reason why we use
angular?
reduced mass?
Why we use reduced mass?
Yeah.
Is that what you said? Well, not really. I mean, we use the reduced mass just to make the math simpler. I mean, the mass. If we didn't use the reduced mass, it would just make the math a little harder. But no, it doesn't. That doesn't really change things significantly.
Oh, is it spin orbit coupling?
Yeah, good. That's one that we ignored. We ignored spin orbit. Yes, we ignored that, and we will talk about that today. We ignored some other ones though too. Can anyone think of any other interactions that we ignored?
Did we ignore any relativistic? Correct?
Yes, exactly. We ignored relativity. Anything else that you can think of offhand?
There's like a interaction between the, I think it's responsible for the hyperfine transitions.
That's exactly right. Hyperfine, that's the spin of the nucleus. Hyperfine, that's a spin of nucleus, and we'll discuss that later. That's exactly right. And then there's other things that we ignore. Like for example, what if there's a B field? What if there's a little magnetic field around? And there always is. Like on Earth, we have the Earth's magnetic field. So there's always a magnetic field on Earth, on planet Earth. So there's always a magnetic field around. But there could also be an electric field too. What if there happens to be an electric field? So these are also perturbations. Some background magnetic field or electric field. Okay, so these are a lot of terms that we ignored. And so these are real terms that actually have important physical consequences for physics in many different areas. And so so we need to treat them. And how do we treat them? We treat them using perturbation theory. And what's going to happen is these interactions are going to cause the energy of the hydrogen atom to go into some new value, En naught plus En1 plus En2, etc. There's going to be some higher order corrections to the energy of the hydrogen atom to the nth level. And so that means, and these corrections we call this the fine structure. So you often will hear that word fine structure. And so when people say fine structure, they mean the energy corrections to the hydrogen atom due to all these terms that we forgot. So let's just go through them one by one. And so the first one that let's start with the relativistic correction. We'll do the relativistic correction, and then we'll do this spin orbit correction. Okay, let's do the relativistic correction. And so for the relativistic correction, you guys already have been introduced to that in the homework. But in the homework, you did the relativistic correction for the square well, which is an easier problem. Now we're going to do the relativistic correction for the hydrogen atom. So remember, we're doing it for hydrogen now. We're talking about hydrogen atom. So, but let's just review the relativistic correction, which you guys have mostly already done. But let's just review it anyways. So we know that for a free particle, for a non-relativistic free particle, then we know we always use kinetic energy is equal to p squared over 2m, right? That's what we always use. But we know that for in reality, when we take relativity into account, relativity tells us the very famous result, which is that E squared is equal to p squared c squared plus m squared c to the fourth. Now that's the total energy of a particle classically, and you guys all hopefully learned that in maybe physics 7c, I think is where you learned that. And so that means then that the energy is equal to, I can write the energy as p squared c squared plus m squared c to the fourth. And so that means that the kinetic energy is just equal to the total energy minus the rest mass energy, E minus mc squared. That is the definition of kinetic energy. And so kinetic energy then is going to be square root of p squared c squared plus m squared c to the fourth minus mc squared. So that's the actual, so that's kinetic energy classically. So that's that's actually classical kinetic energy. Classical kinetic energy. So when we did the Schrodinger equation, we really should have used this. This is right. This is the right way to do it. And p squared over 2m is wrong, okay? So this is wrong, and this is right. So we actually used the wrong formula when we did our quantum mechanics because we forgot about relativity. But of course, the reason we did it is because this formula here is ugly. It's ugly and hard. And you know how physicists are, we hate ugly, hard formulas. Okay, we don't totally hate them, but we try to avoid them because we're intrinsically very lazy. Okay, and so we don't want to deal with it. But now let's deal with it. And so what we're going to do is we're gonna take the new kinetic energy, and then we're going to find h prime, where h is equal to h naught plus h prime. Okay, we got to find that. We want to use perturbation theory, so we must find the correction to h. We need to find the correction to the Hamiltonian. And so that means that we want to be able to write h equals h naught plus h prime. But the question is, what is h naught and what is h prime? Okay, that's critical. So let's figure that out. So we know that kinetic energy is equal to square root of p squared c squared plus m squared c to the fourth minus mc squared. And so we'll just do a little trick. So we'll do this little algebra trick where what we're going to do is we're going to pull mc squared out. So we can write this as m squared c to the fourth times p squared c squared over m squared c to the fourth plus 1 minus mc squared. So I'm just doing some little math tricks, okay, but that's nothing too fancy. But then I see that, oops, let's get this right. And so then I can pull this out. He comes out, and so this is equal to mc squared times, and these guys cancel. And so this becomes p squared over m squared c squared plus 1 minus mc squared. Right, let's see if I do that right. Yeah, that's right. And so then, so this is then mc squared times square root of 1 plus p over mc squared minus mc squared. And so then this
I can't get out of my head. I need to freshen up on like where the hell does this stuff come from. So let's pull this up on the other screen. Yes, I want to read Hagakure, the Book of the Samurai. Okay. Where does the formula E squared is equal to m squared c, p squared times c squared plus m squared times c to the fourth come from? The equation is a fundamental result. Explain very simply how to derive this formula. P squared C squared term accounts for the kinetic energy. M squared C to the fourth term accounts for the intrinsic energy. How is this formula derived? Fuck you. How is E equals MC squared? Might as well just have this on screen. E equals MC squared derivation. I don't want to read this, bro. Let me watch a video. Okay.
In mid-1905, Albert Einstein derived what is the most famous equation in the world, E equals mc squared. But he didn't just write this down out of the blue. It followed directly from his paper on special relativity that we talked about in last week's video. And here's how he did it. Suppose you're watching a cat float freely in empty space, when suddenly it emits a flash of light in all directions. The light carries away some energy. We'll call it E. So by conservation of energy, the cat must have lost energy E. But since the light was emitted symmetrically in all directions, it won't have changed the cat's velocity. So where did the energy for the light come from? Never mind that now. Let's imagine you get bored and zoom off in a spaceship in the middle of the experiment. But from your new perspective, you're sitting still in your spaceship, and the cat is the one moving past outside the window. Therefore, you'll calculate that the cat has some kinetic energy, that is, energy of motion. And when you see the cat emit the flash of light, you'll again measure that its energy decreases by the energy of the light. Except now that you're moving, special relativity tells us that time passes at different rates for you and the cat. So you'll measure a different value for the frequency, and thus energy of the light. This is the relativistic Doppler effect. And for our purposes, it amounts to multiplying the energy of the light by 1 plus your velocity squared divided by twice the speed of light squared. So to recap, if you take off the velocity v, you'll see the cat gain some kinetic energy ke1, then at the flash, you'll see the cat's energy decrease by e times 1 plus v squared over 2c squared. On the other hand, if you wait, you'll see the cat's energy decrease by e, and now when you take off, you'll see it gain kinetic energy ke2. But this is silly. You never touch or otherwise influence the cat in either case, so we should get the same total energy at the end. Rearranging, we see that the kinetic energies before and after the flash must be different. And the kinetic energy of an object is 1/2 of its mass times its velocity squared. But we know that the velocity was the same in both cases. So in order to account for the difference, the cat's mass must change when it emits the flash of light. Now, if we cancel things out, you can see that the change in mass of the cat must be equal to the energy of the light emitted divided by c squared, or as you've heard before, E equals mc squared.
Ah. What a nice video. Okay. Yeah, and then you want to include okay.
Because we're intrinsically very lazy. Okay, with this as plus 1. Right, let's see if I do that right. MC squared times square root of 1 plus p over mc squared minus mc squared. And so then this thing, what are we gonna do to that? You guys have already sort of seen this, I think. What do we do there? What do we do next to that square root thing?
Do a binomial expansion.
Yeah, Taylor, we do a Taylor expansion, that's right. Taylor expand. And so then we see then that the kinetic energy, taking relativity into account, is looking like this. I'm going to do that Taylor expansion, where this is now mc squared, and the Taylor expansion will be 1 plus 1/2 p over mc squared minus 1/8 p over mc to the fourth plus blah 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 blah. Okay, and so then minus mc squared, and so then I see that this times this, these guys are going to cancel, right? And so then I see that my kinetic energy is equal to then I multiply all this stuff out, and I'm going to get my kinetic energy is equal to p squared over 2m minus p fourth over 8 m cubed c squared plus dot 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 dot, and we will ignore all these higher order terms. And then so then what we see is that this then, so we see that I can write now my real Hamiltonian then is equal to p squared over 2m plus my potential energy term for the hydrogen atom. But now I have this new part, p fourth over 8 m cubed c squared. This is my Hamiltonian for hydrogen, for electron in hydrogen. So I see that my new Hamiltonian for an electron sitting in hydrogen is going to be, I'm going to have my kinetic energy term, my old term from here, and I'm going to have my Coulomb, my 1 over r term. But now I have this new term right here. And so that means that I can write H is equal to H naught where this is h naught, but now I have h prime, where this is h prime. So my correction is going to be minus p to the fourth over 8 m cubed c squared. Okay, so now the question is, we have to ask ourselves, okay, so now now with this perturbation, we have to ask ourselves, what is the energy correction to the energy levels of hydrogen? All right, so we want to know En. What is the new En? And remember, we know that the old energies for this, they're negative 13.6 over n squared. So that's the old energy levels, but now we want to know what are the new energy levels. And why, and I should add, why do we care about the energy levels? Why as physicists, why are we going on and on about energy levels? Can anyone answer that question? Why even care about the energy levels? I mean, there's many answers to that question, but just give me one.
The emission and absorption lines come from energy level transitions.
Exactly. That's a good reason, because it determines optical properties. That's right. The optical properties. The energy levels determine basically all the properties, but the most obvious thing is the optical properties, what you just said. So that's good. Yeah, and really, in some sense, it's because we can measure it. Like, as physicists, we can measure energy levels. We're good.
What did he say?
I mean, there's many answers to that question, but just give me one.
The emission and absorption lines come from energy level transitions.
Exactly. That's a good
Emission
reason.
and absorption
it determines optical properties.
lines. Okay.
That's right. The optical properties. The energy levels determine basically all the properties, but the most obvious thing is the optical properties, what you just said. So that's good. Yeah, and really, in some sense, it's because we can measure it. Like, as physicists, we can measure energy levels. We're good at that. And so this is something we can test. We know how to do experiments that measure energy levels. So that's why we're always going on and on about, the energies. Okay, so what are the energy levels? Well, this Hamiltonian, of course, is too hard. I'll just write it here. This is too hard now to solve. Too hard to solve h psi equals e psi. All right, because what we would like to do is just solve the Schrodinger equation, h psi equals e psi, but it's too hard. We can't do that. And so we cannot just by brute force find the energy levels, because that Hamiltonian is too damn hard for us. We're not smart enough. So what are we going to do instead? How are we going to find those energy levels? We're going to use what?
Perturbation theory.
Yes,
Yeah.
That's why we love perturbation theory. It's a tool for people who are not geniuses. Let's see. So here, n naught. So we know that we have the old one, which is the negative 13.6 ev over n squared. But now we're going to have the new correction, en1. And so let's only go to first order. If someone asks you a problem and says, what's the energy? Always just do first order, and see if that's good enough, then stop there. Usually the first order is good enough to give you a sense of what's happening. But sometimes you have to go to second order. Sometimes the first order correction is 0, in which case then you go to the second order. But let's just go to the first order. So good enough. So let's just go to first order. And so it's a simple formula.
Yep.
We know what the formula is.
Yep.
The formula is En1 is equal to, for the nth level, we just take whatever n state we're talking about, and we just sandwich it. We just calculate the expectation value of the perturbation for that state. We just go boom, and it's an easy integral. Well, not always easy, but relatively easy. Easy integral. It's easy in the sense that any integral can be solved.
Yep.
One way or another. Okay, but before we do that, first we have to do a few things. Before we can plug into that nice simple formula, we have to ask ourselves a couple of questions. What's the first question we ask ourselves? Say it.
Is it degenerate?
What? Yes. Is the nth state degenerate?
Boom!
And let's think about that. So here's hydrogen. This is the picture that you've seen a million times. I got my nucleus there. This is the 1 over r potential. And then I have my ground state.
Have I seen it a million times, though? Have I seen it 1 million times, exactly?
E3, you guys have seen this before, and then we get all dense up there, right? So E1 is, I'll call it n equals 1, and I have my n equals 2 state, I have my n equals 3 state. And so if I just pick an arbitrary nth state, like let's say n equals 3, let's just pick n equals 3, this one, a random state. Is it degenerate? Yes or no?
Yes.
That's right. What is the degeneracy? And this is something you learned last semester. How many states are there in that degenerate manifold?
2l plus 1.
Say again?
2l plus 1.
That you need to use that, but there's a lot of else. I mean, maybe I should ask that. What are the else in that? What are the allowed else for n equals 3? Somebody tell me.
I think someone
All
mentioned
like all integers between 3 and -3.
No, although that's close. But remember, L is not a negative number. You were thinking of m though.
Oh, yeah.
So I'm asking about L, not M. So I'm asking about L. So what are the allowed L's for n equals 3?
0 to n minus 1.
Exactly. 0, 1, and 2. It's that pattern that you learned last semester, that weird pattern for hydrogen. So it's the L's have to be less than the n. And so now, but then for each of these L's, there's a bunch of M's for each of those L's. And so that adds up to all the different degeneracy. And so if I have some n, there's a formula for the degeneracy. Do you guys, anybody remember what the formula is that tells me how many degenerate states at a particular n?
I think someone mentioned in the chat that it's n squared, but
Yes,
yeah, that's what you should
exactly.
get all the odd numbers.
Yeah, it's n squared. So it's n squared degenerate. That's right. And so that means it's massively degenerate. That's a big number. I mean, that means like for n equals 3, there's 9 states. N squared is 9. That's a whole hell of a lot. So it's massive degeneracy. Humongous, massive, ginormous degeneracy. Massive degeneracy. Okay, so that's a problem. So now we have to. So that makes us start to feel uncomfortable about this problem. So what's the next question we ask ourselves?
Is the basis we already used one in which the H prime for the degenerate subspace are diagonalized?
Yes. So do we have a good basis? Is it a good basis? A good basis? Question mark. In other words, is the matrix element that connects the m state to the n state equal to 0 or not in the degenerate subspace? So we have to figure this out. So the question is, are these off-diagonal matrix elements equal to 0 or not? So we got to figure that out. And so there are different elegant tricks for figuring this out. But I always prefer, I kind of like brute force. I think it's always, when you're learning something, I think it's always easiest just to do the brute force way. So let's just do the brute force way. And we will learn more elegant tricks later. But let's just do the brute force technique to see. And the brute force technique to check. We want to check this question. The brute force technique is to just calculate the off-diagonal matrix element. Calculate M, H prime, N, and then C. Is it 0? This C, what is it equal? You can just see is it 0 or not. So let's calculate it. And so, all right, so in the degenerate subspace, then we see that the degenerate subspace, the way to, so what
Kind of
so
don't
so
like
then
having it full screen. Having it full screen kind of makes it look like I'm in a Zoom call.
in the degenerate subspace,
So
then this
I want to make it clear I'm watching a
generic
video.
off-diagonal matrix element can be written like this. We can think of it as on the left side we have some
But then
we
it's
have
smaller.
N, L, M, and we have our perturbation, and on the right side we also have N, L, M. But in the degenerate subspace, but one of these is our state.
Okay, there we go.
Let's call it. Let's just call this one our state.
I could just
the
zoom
state we're
in
talking
on
about.
this. Oh, there
And
we
this is
go.
another state. This is meant to represent any state in the degenerate subspace.
It's
So
kind of
for
weird
this
because I
to be
can't
just
see
a generic
the
state in
lecture
degenerate subspace,
now.
I will ask you a question.
Okay, I'll just have it like
What is
this.
the value of N? Is N the same as this N or different?
The same.
Yes, because that is the definition of a degenerate subspace. For the two states to be degenerate, the N has to be the same. Good. But what about the L and the M? Are they the same?
Not necessarily.
Exactly. That is the definition of a degenerate subspace. Because as we just saw, in one subspace here, like N equals 3, I could have L equals 0 or 1 or 2. And for each of those, I could have many different M's. And so there's a whole bunch of different L's and M's that I could have. That is the degenerate subspace. That's what it is. So to do this mathematically, let's call that
Okay.
prime and prime. So this then, this matrix element that I've written represents a generic off-diagonal matrix element in the degenerate subspace. So let's calculate this thing and let's see what it's equal to. And so what I will do is, this is how I'm going to do it. So check it out. I'm going to do a little trick. I'm going to write it like this. We also, all right, so in the degenerate subspace, then we see that the degenerate subspace, the way to, so what we mean, so then what happens in the degenerate subspace, then this M, a generic off-diagonal matrix element can be written like this. We can think of it as, on the left side, we have some, we have N, L, M, and we have our perturbation, and on the right side, we also have N, L, M. But in the degenerate subspace, but one of these is our state. Let's just call this one our state, the state we're talking about. And this is another state. This is meant to represent any state in the degenerate subspace. So for this to be just a generic state in the degenerate subspace, I will ask you a question. What is the value of N? Is N the same as this N or different?
The same.
Yes, because that is the definition of a degenerate subspace. For the two states to be degenerate, the N has to be the same. Good. But what about the L and the M? Are they the same?
Not necessarily.
Exactly. That is the definition of the degenerate subspace. Because as we just saw, in one subspace here, like N equals 3, I could have L equals 0 or 1 or 2. And for each of those, I could have many different M's. And so there's a whole bunch of different L's and M's that I could have. That is the degenerate subspace. That's what it is. So to do this mathematically, I'll just call that prime and prime. So this then, this matrix element that I've written represents a generic off-diagonal matrix element in the degenerate subspace. So let's calculate this thing and let's see what it's equal to. And so what I will do is, this is how I'm going to do it. So check it out. I'm going to do a little trick. I'm going to write it like this. This psi and LM, I'm going to write it like this. I'm going to write, because we know that the wave, well, it's too hard to find it, but we know that the wave function, we know that the eigenstates, the unperturbed eigenstates are equal to a radial part times an angular part. And so I'm going to split up the radial and angular parts because that makes the problem easier. So I'm going to have my radial part, and I'm going to have my angular part. I'm going to call it the LM, the angular momentum eigenstate. And now I'm going to have my perturbation, goes in the middle, and that's going to be negative p to the fourth over 8m cubed c squared. And then here I'm going to have L prime, M prime, and then here I'm going to have R and L prime, because the M's are the same, but the L primes are not. So then what I'm going to do is I'm going to notice that what I have here is, what I can do is I can rewrite this is as equal to negative 1 over 2 mc squared. This is just a little math trick, but it's useful, Lm. And then I can see that this is now p squared over 2m squared times L prime, M prime, and R and L prime. Okay, so I'm just evaluating this off-diagonal matrix element. And so the reason this is a useful thing to write it as is because we know that in a hydrogen atom, or and this is something you learned last semester, in spherical coordinates, let's write this in spherical coordinates. Spherical coordinates, you guys know from last semester, I don't remember, but you once knew that in spherical coordinates, that the kinetic energy operator and the kinetic energy operator can be written like this. Well, let's write all this stuff, Lm. But the kinetic energy operator can be written as negative h bar squared over 2m. I have the radial kinetic energy, 1 over r squared, d dr, times r squared, d dr. It's quite tedious to write all this stuff, but you got to do it. Plus L squared over 2m r squared, L prime, M prime, R and L prime. Okay, so this is just another way of writing kinetic energy in spherical coordinates, and you all did this last semester. You're probably hoping that you never have to see it again, but here it is, your old friend. But the reason why I did this is because this is because look, when this is an operator, right? It's an operator. Now, when this operator hits these guys, these states, we have to ask ourselves what happens. So when this operator hits this ket, L prime, M prime, this is a radial. This is a radial operator. This guy right here. This acts on the radial coordinate. does that part of the operator do anything to my angular momentum eigenstate, L prime?
No.
Does it act on it? Yes or no?
No.
Correct. That's correct. So as far as this guy is concerned, this radial operator is just a constant because it doesn't do nothing to it. How about this though? How about this part? This has
Yes,
some
'cause it's angular.
coordinates to it.
Yeah.
L squared. I'm not gonna write it all out. It's it's like all those dd theta, dd phi, blah blah blah, all that stuff, all that angular stuff. But there's a lot of angular stuff in that L squared. Does that act on this ket, the LM? Yes or no?
Yes.
That's right. Yes, because LM is all the angular information is in there. See, all the angular information is there, and all the radial information is here. So yes, that sucker does indeed operate on LM. But there's a really cute trick, because as soon as it hits that, what happens? As soon as L squared hits that, what does now L squared is a horrifically complicated operator. I'm not gonna write it out, remember, but it's basically the spherical. What do you call it? The spherical Laplacian. Del squared is like all these derivatives. I'm not. It's so horrible.
Does it
I'm not gonna write
commute?
out. It's just too fearsome.
That's the only thing I can think of. I don't
But
know.
all that fearsomeness is gonna hit this guy, and what does it all turn into?
Just scales it by its eigenvalue.
Which is
H bar squared L prime plus 1.
Yeah, that's the beauty of it. That's exactly right. Because this thing is an eigenstate of L squared. That's the whole point. Exactly. And this operator is L squared. So so this guy is an eigenstate of that operator. So that means so that means when that operator hits it, the horrific operator turns boom into the eigenvalue. That's the beauty of it. And so that means that this thing can be written as so then what happens is this thing can come sliding through, and this thing and this whole mess turns into this -1/2 mc squared. How am I gonna write this? Let me check this right. Lm, L prime, M prime, and then here I'm gonna have R and L, and then here I still have this ugly thing, -h, whoops, -h bar squared over 2m, 1/r squared, r squared, d r plus. But now this part gets a little simpler. H bar squared, L prime times L prime plus 1, all over 2m r squared, and then this guy is R n L prime. Okay, so that's how it became a little simpler, and I was able to slide that angular ket all the way through to the other side. But this I cannot simplify any further. Cannot simplify. It's a mess. I mean, it's a hard integral. I would have to actually do the derivatives, do the integral. It's a hard integral. But this one is an easy integral. What is this thing equal to?
Delta function.
That's right. Delta L prime M prime. That's right. But I'm asking you even more. What does this delta function equal? It's a Kronecker delta function. And what does this Kronecker delta function equal in this particular situation?
0.
Why?
Because we just have, we know that we're taking a product of two different states.
Yes, exactly. They're different states. That means that either L prime is different. That means that either L prime does not equal L, or M prime does not equal M, or both, right? That means something is different. One of those two has to be different. Otherwise, they're not different. Because the whole point was to see if we can connect any two degenerate states to any two different degenerate states. So that means that this thing is 0, and so therefore my off-diagonal matrix element is equal to what? The whole thing that we were trying to find.
Oh, 0.
0.
Yes. So the question then is, so now I'll ask you, is psi NLM a good basis? Yes or no?
Yes.
Yeah.
Yeah.
Exactly. Yes. And so that means that we can just plug into the simple formula. And so that means then that our energy, we can just use the simple formula. Use simple formula with this basis. And so let's do it. So that means then that the energy correction due to the relativistic correction, we'll call it delta E n, which is really just the first order energy correction, is equal to this. It's going to be psi n Lm, H prime psi n Lm, where these are just our normal hydrogen wave functions. Okay, so let's calculate that. So then let's calculate it. So the energy correction to the end state is then going to be equal to -1/2 mc.
I am on Instagram for some reason.
Simple formula.
Back it up.
With this basis. And so let's do it. So that means then that the energy correction due to the relativistic correction, we'll call it delta E n, which is really just the first order energy correction, is equal to this. It's going to be psi n Lm, H prime psi n Lm, where these are just our normal hydrogen wave functions. Okay, so let's calculate that. So then let's calculate it. So the energy correction to the end state is then going to be equal to -1/2 mc squared times we got the hydrogen wave function psi n Lm, and we got our, I'm going to write it like this, p squared over 2m squared psi n Lm. Okay, so this is what we have to calculate. That is the energy correction. And I'm just using this convenient notation that we derived already. So this we have to calculate. So this is kind of a hard integral. So how do we calculate this hard integral? Well, what we can do is there's tricks. So I want to show you a trick. It's a very cute trick. So let's do a trick. Let's do this. We'll recognize. I want you to recognize that for the hydrogen atom, I have H naught is equal to p squared over 2m plus, and I'm gonna call it v, where v is just negative v squared over 4 pi epsilon naught r. Okay, that's the Coulomb interaction, but I'm just going to call it v. So I have this is H naught. That's the regular hydrogen Hamiltonian. But that means then that p squared over 2m, the kinetic energy, is equal to H naught minus v, right? And so that means then that if I square these two things, then I have p squared over 2m squared is equal to H naught squared plus H naught minus H naught V minus V H naught plus V squared. And so what I can do then is I can plug this into this. And so then I can see that delta En is equal to negative 1 over 2 mc squared. And now I can just do this very cute trick, because now you see that if I have psi NLM here, and have H naught squared minus H naught V minus V H naught plus V squared psi NLM, then what does this H naught turn into? Because when I calculate
squared.
exactly, because it's going to hit that, thing's going to hit that, and that's an eigenstate of H naught. Exactly. And what is this H naught going to turn into?
En naught.
En naught.
That's exactly right. And so is this guy.
En naught.
And so then this thing becomes a little simpler, because you see it's going to end up equaling negative 1 over 2 mc squared. So and then I'm going to have this. I'm going to have En naught squared. That's this term. That's the easy one. And then these two guys are the same. So that'll become minus 2 E naught. And then I'm going to have the Coulomb constant E squared over 4 pi epsilon naught. And then I'm going to have psi NLM. But I still have this difficulty of figuring out the 1 over the expectation value of the 1 over R operator. Plus, and then I have the other one, which is going to be E squared over 4 pi epsilon naught squared times psi NLM. But now it's 1 over R squared times psi NLM. Okay, and so I just did this little trick, this little manipulation, and so now this becomes an easier problem. And there's further tricks to calculate, because this thing, I will call it, is the expectation value of 1 over R squared, and this thing is the expectation value of 1 over R for the M state. And these things can be calculated, and so these are homework problems. So I'm not going to work them out, but you can calculate these things without too much difficulty. And so then when we calculate them, what we find is that the energy, the correction to the nth term, the relativistic correction, is equal to negative, when you work it all out, you're going to, this is the answer that you get. It's going to be E naught squared over 2mc squared times 4n over L plus 1/2 minus 3. And so you see what's going to happen is it's going to, it removes the L degeneracy. And so in other words, if I had, for example, if I have the n equals 2 state, then I'm going to have 3 L equals 1 states, right? Because that's going to be m is equal to 1, 0, minus 1. And then I'm going to have 1 L equals 0 state. And so you can see then that what's going to happen is it's going to leave the L equals 0 state alone. Calculate then what we find is that the energy, the correction to the nth term, the relativistic correction, is equal to negative, when you work it all out, you're going to, this is the answer that you get. It's going to be E naught squared over 2mc squared times 4n over L plus 1/2 minus 3. And so you see what's going to happen is it's going to, it removes the L degeneracy. And so in other words, if I had, for example, if I have the n equals 2 state, then I'm going to have 3 L equals 1 states, right? Because that's going to be m is equal to 1, 0, minus 1. And then I'm going to have 1 L equals 0 state. And so you can see then that what's going to happen is it's going to leave the L equals 0 state alone, but then it's going to take these 3 L equals 1 state and it's going to split them. They're all going to go to different energies. So that's called splitting the degeneracy. It removes the degeneracy. So this we call splitting. It splits these guys, the L's, and because you can see the L is right there. So the perturbation looks at that L and says, oh, you have a different, if you have a, oh, actually, I'm sorry, I screwed this up. It doesn't depend on the M sub L. Oops, sorry, let me just rewrite that. What it's going to do is it's going to split the L. So this is the split. Okay, so it did not remove the M sub L degeneracy. It removed the L degeneracy. So these 3 guys are still degenerate, but they are no longer degenerate with L equals 0. So the L equals 1 and the L equals 0 states are split. Okay, so that was, I'm sorry, I said that incorrectly. Okay, so that's basically what it does. And so now let's move on to the next topic, which is spin orbit coupling. Okay, so let's talk about spin orbit coupling. And so spin orbit coupling, this is actually very important. It plays a big role in atomic physics, and it also plays a big role in condensed matter physics. So when you talk about the physics of materials, solids, crystals, this spin orbit coupling plays a big role. So it's a very, and it also, I should say, for chemistry too, because it's gonna play a big role in chemistry too, because it's gonna determine a lot of properties of molecules. So spin orbit coupling is a very important topic. It's not just some weird little thing that we play with in our quantum mechanics class. It actually plays a very important role out in the real world. So this is a useful thing to understand. Okay, so what is it? So spin orbit coupling.
I love that preface, man. This preface is so important. This preface is so important for just priming the mind to listen and be interested.
So
and
let's talk about spin orbit
absorb.
coupling. And so spin orbit coupling, this spin orbit coupling plays a big role. So it's a very, and it also, I should say, for chemistry too, because it's gonna play a big role in chemistry too, because it's gonna determine a lot of properties of molecules. So spin orbit coupling is a very important topic. It's not just some weird little thing that we play with in our quantum mechanics class. It actually plays a very important role out in the real world. So this is a useful thing to understand. Okay, so what is it? So spin orbit coupling, it's sort of a little bit of a tricky thing if you've never thought about it before. And so this is the idea. So normally we have this. This is a hydrogen atom. we have a nucleus and we have the electron going around it, and the nucleus is just sitting there. But now to think about it, let's do this. Let's move into the rest frame of the electron. And when we sit in the rest frame of the electron, then we can think of the proton is now circling the electron. Because if you're standing on the electron, what you see, you think that you're still, and then you see the proton going around you. So in this new picture, I have my E minus, and now I have my proton going around. And in this, I have a way to think about it is that now I have a ring of current creates a B field. So you can just see that there's a B field. So because that I have a ring of current, because you guys know that if you have current flowing in a circle, then that's a solenoid, and you always get a B field in the center. Yeah, you guys remember that from E&M, right? You have current, use the right-hand rule, and then you get a B field. And so that means that this, you can see how this electron, he feels a B field due to the fact that the proton is creating a B field. And that means then that there's an energy. And to find the energy, so to find the energy, we always use the classical Hamiltonian. Remember, when we're talking about quantum mechanics, we always use classical mechanics. We start with classical mechanics. When we derive the Hamiltonian, it's always classical. Then we turn our classical terms into operators. That's the rules of quantum mechanics. So what we have to do is we have to first analyze the situation classically, and then we go to quantum mechanics. So classically, the energy, the Hamiltonian, classically the Hamiltonian, if I have a B field and the electron feels a B field, do you guys know what the Hamiltonian is? Where's the energy coming from?
The interaction between the dipole and the B field.
Yeah, exactly. Because there's if the electron is just sitting there and not moving, then there's no energy. But it has a dipole. So it's going to be the energy is negative mu dot B, where mu is the dipole of the electron, and that's the classical dipole energy. And the dipole of the electron is, you guys know, for any particle with spin. We talked about this at the beginning of the class. You have the G factor, the charge, 2.
I was not listening.
When we derive the Hamiltonian, it's always classical, and then we go to quantum mechanics. So classically, the energy, the Hamiltonian, classically the Hamiltonian, if I have a B field and the electron feels a B field, do you guys know what the Hamiltonian is? Where's the energy coming from?
The interaction between the dipole and the B field.
Yeah, exactly. Because there's if the electron is just sitting there and not moving, then there's no energy. But it has a dipole. So it's going to be the energy is negative mu dot B, where mu is the dipole of the electron, and that's the classical dipole energy. And the dipole of the electron is, you guys know, for any particle with spin. We talked about this at the beginning of the class. You have the G factor, the charge, 2m times the spin. So that's for a charged particle with spin. And so for an electron, Q is minus E, and G is the G factor is 2. And so the magnetic moment of an electron is minus E over m times s, the spin of the electron. And so that means then that H is going to be equal to E over m times s dot B. Okay, so that's going to be the energy. So then the question then, of course, is what's B? Okay, so that's the idea. The idea is that an electron in hydrogen, it feels a B field. There's a B field that it feels, and that B field leads to this this energy term, this interaction. But the question is, what's the B field? And so to derive the B field, I like to do it a different way. Let's do it a different way. Because the thing is, there's always two ways to do spin orbit coupling. One way is what I was just talking about. You go into the rest frame of the electron, and then you have the proton spinning around you. I don't like this way. Mike doesn't like. And so there's another way of doing it, which I like more. And often you see both ways. Some classes you do one way, some books you do the other way. There's always two ways. But now I'm going to show you the other way, which is better. It's better for a number of reasons that I won't get into. So the better way is to think about it like this. Let's consider it differently. Let's do it differently. Here's the deal. If I have a charged particle, if I have some electric field, and I have a charged particle, Q, with some charge and some velocity in my electric field, moving through an electric field, then using relativity, then there's a relativistic relationship. And if you know relativity, then you know it. If you don't know relativity, then you don't. And I'll just tell it to you. But using relativity, then in the rest frame of the charged particle, the particle sees a magnetic field. And that magnetic field is equal to negative gamma over c squared B cross E. And that's a very important result. And gamma, of course, is the famous relativistic gamma, 1 over square root of 1 minus v squared over c squared. And so if your velocity is slow, then gamma equals, somebody tell me, what does gamma equal for in the non-relativistic limit? Yeah, 1. That's right. Gamma equals 1. Okay, so a lot of books and people don't use this derivation because it requires you to use this funny result from relativity that most people sort of don't remember unless you use relativity a lot. However, I like to use this result because this is really a much more general and better and actually more correct. It's a better way of doing it. You can generalize the treatment to many different situations, which I won't get into, but which I've seen in my career. Okay, so using this treatment, if you buy that this magnetic field is there, then it becomes really simple because now you then see that you can then just say that the Hamiltonian is equal to negative mu dot B, which is equal to E over m s dot B, where this now becomes the B. And so that's what we're going to do. But let's do some little manipulations first. But let's do a little bit of math. Let's do some math tricks first. And so the first math trick that we'll do is we'll say, we'll use this gamma equals 1. And so we see that B is equal to negative 1 over c squared V cross E. And so the first thing that we'll do is we'll rewrite the V. And so we see that's negative 1 over c squared times P over M. All right, I just rewrote the J as P over M. I can do that. And now I'm going to do another little math trick. I'm just going to reverse this order. So that's going to be equal to 1 over MC squared E cross P. Okay, just a little math trick because when you reverse the order of a cross product, you get a negative sign. Okay, and so now I'm going to do something else. Okay, so now what I'm going to do is I'm going to take this B and I'm going to plug it into here. And so now I see that the Hamiltonian is equal to E over M times S dot this thing, which is 1 over MC squared times E cross P. Okay, so that's my Hamiltonian, and this is all classical. I haven't even done any quantum mechanics yet. But what we'll do is, but now we're gonna do a little trick. Let's find E, and so we know that E is this. It's just the Coulomb potential of the nucleus of the proton, and so we know that E is just a simple Coulomb term, which is gonna be E over 4 pi epsilon naught r squared times r hat. Okay, and so this is a formula that you guys should. This is just a Coulomb formula that you guys should remember from electricity and magnetism. It's the 1 over r squared fall off of the electric field. But I'm gonna rewrite it a different way. I'm gonna remember that r hat is equal to r over r. And so that means then that I can write E is equal to E over 4 pi epsilon naught times R over R cubed. Okay, and that's just the Coulomb term, just rewritten maybe in an unfamiliar way. And so now I'm going to plug this into there. And so I see now that my Hamiltonian can be, let's collect all the terms out in front. It'll be E squared over 4 pi epsilon naught times 1 over M squared C squared R cubed times S dot R cross P. Okay, you guys see that? Just plugged in. And so remember, this R here is the same as this R. That's where the R came from. Okay, but now let's do the big cute trick, which is to notice that this R cross P is just another way of saying what? Yeah, L, angular momentum. L, angular momentum is R cross P. And so that means then that I can replace that this is L, but there's also one other thing. We need a factor of 1/2. And the reason for that is because we're in an accelerating reference frame. And so I did sort of trick you at the beginning because this result is for a non-accelerating frame. But actually, you know that in the hydrogen atom, the electron is actually accelerating. It's in this because it's going in a circle, right? And so there's this little trick, and I'm not going to derive it, but because it's but there's just this little funny factor of 1/2 you need because you're in an accelerating frame. So let's plug that in, and so then what we get is this: H equals, then you get your result: E squared over 8 pi epsilon naught times 1 over M squared C squared R cubed times L dot S. And I just reversed the order because L and S commute. And that's something we already knew because this is acting on the spatial variables and this is acting on spin. And they're different. And so those operators commute. Okay, so I just reversed the order. It's okay, I can do it. And so this was all done classically using classical reasoning. But now, so that means that in quantum mechanics, then I've just derived the spin orbit energy correction, which is that the spin orbit energy, and I put the little prime here just because the perturbation is equal to then, I have a radial part times L dot S, where this radial part is just a function is going to be my E squared over 8 pi epsilon naught times 1 over M squared C squared R cubed. Okay, so that's my spin orbit interaction. It's just a radial part times L dot S. And maybe I will just erase this little dot because that's not a dot product. It's just a multiplication. Okay, so that's the spin orbit interaction. And so now what I'm going to ask you, the question is, how does this affect the energy levels of hydrogen? What is the change? What is the change in the energy levels of hydrogen that is due to the spin orbit? And sometimes when people say spin orbit, they just do L dot S for short. So that's spin orbit. Sometimes people just say L dot S and leave out the radial part just as shorthand, just to say, hey, I'm talking about the spin orbit interaction. So what is the change in the energy levels of hydrogen due to the spin orbit interaction? That's the question. And so to answer that question, we have this new Hamiltonian. Hamiltonian is equal to, I got kinetic energy, I got my potential energy, but now I have plus my spin orbit. I got a new interaction in my Hamiltonian. But this is my old Hamiltonian, H naught, and this is my new perturbation, spin orbit. And so to answer this question, we're going to use what?
Perturbation theory.
Exactly. So to answer this, we're going to use perturbation theory. And so that's what we'll do next time. But the big question that we're going to have to ask ourselves is, do we have a good basis? And that's the question that you have to ask yourself. And then if we don't have a good basis, what are we going to do? Do we have a good basis? That's the big question. But we'll discuss that next time. And so that's it, guys. Orbit energy. And I put a little prime here to color an accelerating frame. So let's plug that in. And so then what we get is this. H, because first the order mechanics, N times L dot S is the spin orbit energy correction, which is that the spin orbit energy, and I put the little prime here just because the perturbation is equal to then, I have a radial part times L dot S, where this radial part is a radial part. E squared over 8 pi epsilon naught times 1 over M squared. I will just erase this little dot because that's not a dot product. It's just a multiplication. Okay, so radial part L dot S. And so now what I'm going to ask you, the question, the change, and sometimes when people say spin orbit, they just do L dot S for short. So potential. A lot of books and people don't use this derivation because it requires you to use this funny result from relativity that most people sort of don't remember unless you use relativity a lot. However, I like to use this result because this is really a much more general and better and actually more correct.
Okay. Damn, this guy does a lot of math.
All right, we're being recorded. Now we'll do the little trick. Is to discuss spin orbit coupling, as well as a new trick for a new perturbation trick, which allows us to, which helps us to find the good basis, which we'll discuss more very shortly. And so,
Okay, so all of this isn't even touching on the thing that I actually have to learn, which is fine structure, hyperfine coupling, and variational method. I do want to go through these today, though. What are my homeworks even touching on? WKB, WKB, half harmonic oscillator. Okay, so all my shit is dealing with WKB anyway. Fuck. Okay. Okay. If you insist. Hey, if you insist. Let me see if the lecture video has uploaded yet. Nope, not yet. What date was Wednesday? Google Calendar. Wednesday was the 28th, and this video was uploaded. I can't see when it was uploaded. It just says that this is the 28th. Okay, whatever. Okay, WKB approximation. Should I just watch this then to try to understand? I feel like he's going to be talking about a whole bunch of complicated shit though that I won't be able to understand. Maybe I'll be able to get it though. Why is it lagging now? Hello? What's going on with my internet? Internet seems fine.
let's see. So today, our plan is.
Bro.
Kramer's and Brillouin. Actually, they're famous for other stuff too, these guys.
Let's see.
And the WKB. See, that's it. That's it. Because then I could just say,
Okay, it doesn't seem like it'll be too bad.
Today,
let's just
our plan
watch
is to
it.
discuss WKB
You never know
approximation,
until you
and
watch
it stands
it.
for three names. Wendell or Wenzel. Nobody remembers these guys' names. Wenzel, Kramer's, and Brillouin. Actually, they're famous for other stuff too, these guys. These were three smart dudes. Okay, so WKB approximation. And so this is a new topic. And it's a new approximation method. And I started to introduce it in the last lecture, but I'll just kind of introduce it again right now. The idea is that we've already been discussing two approximation techniques, which is perturbation theory. And this is, we found is pretty useful when you can write your Hamiltonian. I mean, the whole point, first I just want to say the whole point is you want to solve the Schrodinger equation, okay? That's the whole point, is to solve that equation. And the only question is how to do it. And so for perturbation theory, we see that if we can write the Hamiltonian as a known Hamiltonian plus a small perturbation, then it's useful. Then we use perturbation theory and all the tricks of perturbation theory that we've discussed. On the other hand, we also learned the variational method. And the variational method did not care the size of the Hamiltonian or perturbation. The variational method was simply a very clever trick for basically finding the ground state. It's good for getting the ground state. And you can get a limit. The variational principal limit is always greater than or equal to the actual ground state.
Yeah.
So it's upper limit on the ground state energy. Okay, so that's good. But now we're going to do a new one, which is called WKB, named after those three guys. And this is useful for when we have big energy, or in other words, short wavelength. And the idea is that the potential is slowly varying, and then it works pretty good. In other words, if I have some potential that looks like this, that's my v of x, and my wave function is here. See, there's my wave function. So you can see a slowly varying potential with very short wavelengths of my wave function. So then WK is good. WKB is good. Okay, and so so today I'm going to go through WKB, and I just want to say that the utility of these approximation methods, I sort of did them in priority of this class. The perturbation theory is the most important one. Then variational principle is pretty important and quite useful. And I would put this WKB in third place. I think it's not as useful as the other ones, but it's still quite useful and it pops up a lot. And and it gives you a useful way of thinking about the Schrodinger equation. So it's really worth thinking about and going through. And so there's different ways to derive it. There's like a fancy mathematical way. We're going to do that. But before doing the fancy mathematical way, let's just think about it intuitively, because the idea of the WKB approximation is very simple, simple. And so I want you to understand the simple thing, and then we'll do the more. You can always derive it using complex mathematics. But let's try to understand the simple way. And so the thing to remember is that let's consider a constant potential. A constant potential. Then we have this, like a square well. All right, but that's minus v naught. And so then you see if I have so then you see that if I have some energy here, E for the particle, then you guys know how to get the wave function. You guys sort of know what to do. You guys know that you've done this problem before, and so you know that to get to solve h psi equals e psi, then you guys know that h is equal to negative h bar squared over 2m d squared dx squared plus p of x psi. Oops, sorry, shouldn't have done that. And then you can say h psi times psi is equal to. I just want to not write so much. Okay, so that's the problem. That's what you got to solve. And so you guys know that if v is a constant, then this becomes really easy because it's negative h bar squared over 2m d squared dx squared. Then you're gonna have this v. Let's see, we'll do that plus v minus v. Let's see what's the best way to solve this. Plus v. Well, I don't know. Let's plus v psi equals e psi. And you guys have all done this before, and you know that. Then you can write. You know that if psi is equal to e to the ikx, a wave, a plane wave, then you plug that in, and then you get you end up with e is equal to h bar squared k squared over 2m plus v. And so then you know that you get your famous k is equal to square root of 2m e minus v over h bar. All right, so you've all done this before, right? And so then you know that so that means that if you see that if the well is deeper, so deeper well, then what does k do? So if the well is deeper, then what happens to k, your wave vector?
Increases.
That's right, because v is a negative number and it's minus a negative number, so k increases. So k is bigger, and if k is bigger, what happens to your wavelength? Bigger k means what happens to the wavelength?
2 pi over lambda.
Smaller wavelength. Lambda smaller. Okay, this is intuition that you got last semester or even earlier in Physics 7C. Okay, and so you just kind of know that for these square wells, then the solution of the Schrodinger equation is this very simple plane wave. But now what I want you to do is to think about that solution a little differently, because here, so we can see then that inside of this square well, we have this solution, which goes as psi e equals e to the I kx, right? Now, what you would normally do to solve this correctly, and you did do this last semester, is you would match everything to the boundary conditions, and you look at all the different possible solutions and match them very carefully to the boundary conditions, right? That's what you did. But let's not go through all that bother. Let's just notice that this function, let's not worry about the boundary conditions so much, but let's just notice that function solves the differential equation. And let's take a closer look at this function, e to the I kx, and let's notice that that's the same as e to the I phi of x, where phi of x is a phase.
Mm-hmm.
And obviously phi of x in this case is equal to kx, right? E to the I kx. But phi of x, I can think of it like this. It's an integral from 0 to x of k dx prime. And why did I do that? I want you to think about the solution of the wave function a little differently now. Rather than just coming up with these functions, that whatever function, like Bessel function or whatever, or plane wave, rather than coming up with this function, I want you to think about it in terms of a phase. And so I want you to think that the solution, to get the solution, then if we start with some phi, a known phi, like if we know the phase at, say, here, 0, at some starting point, x equals 0, then to get the wave function at some further x, then to get psi e of x, then you just have to wind the phase, which means psi e of x is equal to e to the I 0 x prime. Oops, missed that. 0x k dx prime, where this is the phase. And so I'm just taking a very simple solution and I'm sort of making it more complicated. I'm like sort of recasting it in like a different language. But this different language is very useful. And so the way to think about it is that there's a little wheel. Like no, that was actually not useful. Let's not do it like that. Let's do it like here. Let's think about there's a little wheel that's rolling. It's a little wheel. And that wheel gives the phase. And so think of the wheel as literally rolling in space. The wheel rolls in space. And so the phase of the wheel is this. The phase of the wheel, because the wheel is literally rolling. And so this is, an arrow that goes to the circumference of the wheel. This angle is phi. And so then I can see then that phi, if the wheel is rolling, then the phase is equal to the circumference, or it's like the distance it's rolled, divided by, can you guess, divided by what? A wheel is rolling. It's actually a very simple geometrical question. It rolls some distance, x some distance, and what's the phase? What is the phase change of the wheel if I just sort of pick one point on the wheel and say, I'm following the angular change of that speck on the wheel? The phase is distance divided by what?
Is it circumference?
Close. No, the distance is like the circumference. Okay.
2
It's,
pi.
no, yeah. You're good. You're dancing around. It's like circumference is equal to 2 pi radius. That's correct. But no, that's not what I'm talking about. I'm talking about the angle. The phase is the angle. What's the definition of an angle? You have the arc length. That's the distance. Angle equals arc length divided by what?
Radius.
Yeah, that's the definition of angle. It's distance, which here is arc length, divided by radius. So you guys all know that. I know that you all know that. And so that's equal to x over r. But here the thing is, let's think of the radius of the wheel is equal to 1 over k. 1 over k. And so that means that phi is equal to, if the radius is 1 over k equals r, then 1 over r equals k. That's kx. All right, so I just want you to see that. So the radius of the wheel is 1 over k. And so if that little wheel is rolling, then the angular evolution of that wheel literally gives you a phase. All right,
Huh.
R. Okay? The wheel, if I just sort of pick one point on the wheel and say,
Interesting.
about arc length, you guys all know that. I know that you all know that. And so that's equal to x over r. But here the thing is, let's think of the radius of the wheel is equal to 1 over k. 1 over k. And so that means that phi is equal to, if the radius is 1 over k equals r, then 1 over r equals k. That's kx. All right, so I just want you to see that. So the radius of the wheel is 1 over k. And so if that little wheel is rolling, then the angular evolution of that wheel literally gives you the phase. All right, that's just another way of recasting the solution you already know. And so the little rolling wheel gives phase. Okay, and the wave function psi e of x is equal to it's going to be e to the I. So your starting point 0 to x k dx prime is equal to e to the I kx. You see that? Okay, just another way of writing it. And the phase, the distance, this phase is the integral from 0 to x of k dx prime. Okay, so I hope that you can kind of see that. And so now, if I let's do a more complicated case. So now you can see that if I have, using this kind of idea, if I have a weird potential like this, and now if I put my energy here, and this is my, let's just say that this is my potential, right? And this is x. Now I'll call this x1, and this I'll call x2. Let's see, I'll call this v1. I'll call this v2. Then you can see that when using the same reasoning, then I'm going to get some. If I have this energy, then in this region, I'll call this region 1, and I'll call this region 2. Then in region 1, what's k? K is equal to what? Tell me.
Square root 2 times e minus v1.
Right, because you said v1 is negative because it's down below.
A plus v1.
Yeah, so we'll call plus v1. Or we'll do it like that, over h bar. That's good, yeah. And so that means that in this region 1, the wave function has some wavelength, yeah? And that phase, and so if I start here with some phi at 0, then I can see that in this region, if I try to understand my wave function, by this little wheel that's rolling, then I can see that it's e to the I integral from 0 to some x prime k, and that's k1 dx prime. So the little wheel is rolling, and that's going to be the phase in this region 1. I'll call that phi 1. But then once the little wheel hits the second region, what happens in this region 2? What happens to now I have k2 is equal to square root of 2m, and now it's going to be e plus v2 over h bar. And so what happens to the wavelength in region 2? What happens to the wavelength in region 2? Is it bigger or littler?
Longer.
Yeah, because is k bigger or smaller?
K is smaller.
That's right. Why don't you just see that? That's right. And so now it gets longer, see? Like that. And so what happens to the size of the little wheel that's rolling? The wheel is rolling. But what happens to the wheel in this region, region 2? Is the wheel bigger or littler?
It gets bigger.
That's right. It's not a bigger wheel rolling in region 2. And so then I'm going to have here phi of x is equal to integral x1 to x, wherever that is. This is k2 dx. And is equal to square root of 2m. And now it's going to be e plus.
Is it going to be so smaller because
happens to the
k
wavelength
is
of region 2?
larger?
Is it bigger or littler?
Or the
Longer.
wave?
Yeah, because is k bigger or smaller?
K is smaller.
That's right. Why don't you just littler?
So the wavelength will increase. Right? The wavelength will stretch out, so it'll increase because k is getting smaller because v2 is now a higher value. So e plus v2 will give you a bigger number. Okay. Yep.
Like that. 2 to x, wherever that. You see that the psi of e at some x, let's say x is greater than x1, then the wheel rolls through region 1, and it's going to be e. It's going to be basically e to the I. The whole point is that it's the whole total phase at the point x, which is going to be e to the I, all the phase that we get from the first one, which is going to be 5x1 plus the delta phi from x2 to x1 to 2 from x2 to x2 from x1. So so what you can see then is just going to be e to the I k1 x1. Shoot, I keep screwing this up. E to the I k1 x1 plus k2 x minus x1. Should be linear next time. X times x1. Yeah. Okay. So I want you to get that concept of like that rolling phase. And so this is the total phase. Total phase accumulated by rolling wheel.
Quick bathroom break. Fuck, dude, these videos are long. It's like an hour to get through it, man. That's okay, though. Because we're quantum mechanics pros, right? Yeah. I'm very tired. Okay, nice. It's solidified again. I microwaved butter in the microwave, of course. Where else do you microwave things? I microwave butter in my industrial scale radiation machine where I emitted microwave radiation. No, I microwave butter, and then like I microwaved it for too long. I did it for 30 seconds. There's a whole stick of butter. I did it for 30 seconds. And I thought it would just, I thought a little bit of it would kind of like just soften. I wanted to just soften it so I could spread it on bread. But it ended up just like melting almost the whole thing. And so it was just like a pool of melted butter with like a stick of butter that's just kind of like, flopping around. So I just had it like sit down to like hopefully harden back in the butter. And it's back in the butter. It's solidified. So I don't know butter chemistry, but you know what? Seems legit to me. Seems legit to me. Oh my god, I just opened up BeReal while it was like fucking when the notification just got sent out.
But the radius of the wheel changed from different locations.
Let's refresh our brains with a little Twitter. With a little Twitter.
sure we're going the right way? Hila, are you sure we're going the right way?
I need me 10 Big Macs right now. Stat. Dude, I need to start next week I need to regularly work out again and combine it with cardio so that I can just eat. Because eating is so important to me, man. I need to be able to eat to like chill out. And I know this sounds so bad. Like okay, I'm gonna take my multivitamins and I'm gonna eat healthy foods and run so that I can do cocaine and ketamine, okay? Because I really need my ketamine. So I need to live a healthy lifestyle so I can balance it out with ketamine. I know this is what it sounds like, okay? But listen, we all have our vices, okay? I'm over here fucking learning so much goddamn physics and math that I need some vice, okay? I need a vice. I don't have drugs. I don't have Adderall. I don't have Vyvanse. All I have is food. Okay, I got peanut butter. I got bread. I got butter. Okay, that's all I have. Just let me have one thing in my life, please. Okay. Let me have them. Let me have them.
Because the radius of the wheel.
Let me at him. Let me at him.
But k is square root of 2me minus v over h bar. So if the potential changes, then the radius of that little wheel changes. Okay, and so the main point that really drove me into the ground is that the function. So now what we can do, let's do a harder problem. Let's consider this. Here's a square well, which you guys have all done. And now I'm giving you a harder problem. I'm saying, what is the wave function if I have my energies here, and this is my potential, v of x. But now for my potential, I'm gonna do this. I'm gonna say, what happens if my potential does this? Now I'm giving you this really weird potential, okay? So now this is my potential. I just this weird, I put this weird bulge on the bottom. So it's this bizarre function that you've never seen before, just some weird function, v of x. And I'm asking you, what is the wave function, psi e of x? And all that I'm giving you is v of x. And suppose I'm saying that, and so then what would be your best guess as to the wave function? Can you guess a wave function? And I want you to think of I want you to think that the wave function starts with some starting point. I'll call it psi of 0. But then the phase of the wave function evolves as because you can think of a little wheel is rolling from the starting point, and it rolls and rolls and rolls. But the radius of the wheel is fluctuating because the k is changing. And so here I'll give you a hint. The wave function at any point x inside of this well is going to be e to the I phi of x, where that is the accumulated phase of the wave function. And so I guess my question should be then to you, what is the accumulated phase? Because that is the wave function. Do you see how to think of it like that? So this is sort of like a different way for you to think about it, but it's a useful way to think about wave functions. So
we have to integrate.
Okay, good.
Like k with the x, it will be a function of v of x.
That's right. And we have to integrate over the x prime, right?
Yeah, up till x.
Yes. And now I'm asking you, what is this function k of x prime?
The root 2m times e minus v of x over h bar.
Yeah. You have just invented WKB. See, that's it. Because then I could just look at this thing, I could just say, hey, you give me this weird potential with some v of x, and you say, what's the wave function at some particular energy e? And I'll just say, well, I'll just wind my phase to that point. And it's just going to be e to the I integral from 0 to x, k of x prime, dx prime, where k, of course, is this thing, k of x prime. Yeah, that's it. So now, of course, that's really a gross approximation to the wave function. What are we missing when we do this? Can you guess what we're missing?
The amplitude of the wave function?
Well, yeah, but it's sort of like, that's right, but it's kind of like we're missing reflections. Because what's happening is you have waves going in and then the waves are reflected. And so you're sort of missing the quantum interference. You're sort of oversimplifying the quantum interference. And when you really solve the differential equation correctly, what you're doing is you're really taking into account all of quantum interference. So I'll just say this neglects some reflections and quantum interference. And that's why it's only an approximation to say that. Okay, so that is the concept of WKB. And so now what I want to do is let's actually derive it. So that was just all hand waving and talking about little wheels. But I think that it's useful to think about little wheels because like now we're gonna do some equations, and equations will make you feel better because equations always make us feel better, make us feel more secure. But then in the long run, you will forget the equations. But maybe, if lucky, you will remember the little wheel because that's how people are. Okay, so let's derive it. Let's derive WKB. But then in the long run, you will forget the equations. But maybe, if lucky, you will remember the little wheel because that's how people are. Okay, so let's derive it. Let's derive WKB. And WKB. So here's the thing. So we're given some weird v of x, some weird potential, and somebody says, solve the Schrodinger equation. That's what they say to you. Solve it, damn it, solve it. All right, and you're like, oh, okay. How do I do it? And so you already have other.
If you want better.
God, I need to play Final Fantasy VII Rebirth. Fuck, there's so many games, man. So many games, and if I just got off of Twitter and YouTube, my life would be so much like I could just fill it with valuable things like books, movies, and like really good games. Because I value good games, okay? If you don't value good games, then fuck you. Okay? A really good games. Play Metal Gear Solid, the original one. Play the original Metal Gear Solid. The gameplay sucks, but just, you know, get through it and like listen to the story, okay? And it's really good.
Other techniques, you know, that you've developed, but now I'm going to show you a new way to solve the Schrodinger equation. So the new way of solving it, the WKB way, is to do this. Let's assume that the wave function psi of x is equal to some function a of x multiplied by e to the I s of x. where this is some phase. S of x is a phase, okay? And this is completely general, so there's no approximation here. Because any function I can write in this way by the appropriate choice of a and s. Okay, so this is completely general. And so now let's plug this in, plug it into h psi equals e psi. Okay, where h is equal to our old friend negative h bar squared over 2m d squared dx squared plus d of x. Okay, so we plug this assumed solution into the wave function, into this Schrodinger equation. So we hit it, and then so to calculate h psi, there's a little bit of algebra that I'm gonna skip. And then after doing the algebra, this is what you get. You get this, and it's not hard. You guys go do the algebra on your own. D squared, because there's just some derivatives in there, right? Just some little bit of work. You're gonna get the second derivative of a of x plus 2i times partial derivative of a with respect to x times partial derivative of s with respect to x plus I times a of x times the second derivative of s of x with respect to x minus a of x times ds of x with respect to x squared plus k squared a of x equals 0, where k is defined as our old friend square root of 2me minus v of x over h bar. So that's a function of x. Okay, so k is a function of x. Okay, so this is just straightforward. I just plug this assumed solution into it. But now I notice that I have two parts. I notice that it's a complex equation. I have a real part of my equation plus an imaginary part, I equals 0, right? In my differential equation up above, you can see it. So where's my imaginary parts? Like here's the imaginary part, right? I got a little I there, I got a little I there. And the real part is all the other stuff. Okay, so that's pretty easy to notice. And so what can I do now? I got a real part plus the imaginary part equals 0. What do I do next? Can you guess? We're doing math now. We want to solve this equation. What do you think I'm going to do? You've seen it before. To continue.
Set them separately to 0.
Yeah, exactly. Because if it's a complex number that equals 0, then that means that the real part has to equal 0 and the imaginary part has to equal 0. So I'm going to set these both equal to 0. That's exactly right. And so that's going to give me two equations. And so those two equations are going to be as follows. I'm going to have equation 1. Then I get two equations. And equation 1 is going to be second derivative of a with respect to x minus a times second derivative of s, first derivative of s with respect to x squared plus k squared times a equals 0. All right, so I think you can see it's there. Okay, you see it. And then the second equation is going to be 2 times dA dx times ds dx plus a second derivative of s with respect to x equals 0. All right, and so now it turns out that the second equation can be solved. It turns out, and I'm not gonna
Did his lights just turn on?
And so now can be solved.
The exposure.
It turns out, and I'm not gonna figure out. I'm not using some clever differential equation technique. It can be solved, and so let's not worry about how to solve it. But let's just look at the solution. You can just say, oh, I guess the solution, and plug it in and see if it works. So you should see if it works. But this is the solution. The solution is a of x equals c.
After this. So watching WKB, I think that'll be enough to just give me some. It'll give me enough to have an idea of what's happening, but I don't think it'll be enough to
over square root of ds.
Fucking figure out anything
so
for the homework.
This works. If I plug this into equation 2, it works. But notice I have two equations and two unknowns. So this just gives me one of the constraints, but I need another one, right? Because I basically, remember the whole point of this whole thing is that I got my wave function psi is a of x times e to the. So the whole point, I'll just rewrite it here. Psi equals a of x times e to the I s of x. So we want that and we want that. Okay, we want a and we want s. So we're trying to get them. So right now we have a constraint on a and s, but there's two unknowns, and so that's just one constraint. So I need the second constraint. So equation 1 is harder, and there's equation 1 up above, and it's harder, and so it's too hard. Equation 1 is too difficult because which is not unexpected because it's the Schrodinger equation. It's hard, and so we're going to make an approximation, and this is the whole crux of the matter. We're going to make an approximation, and this is the WKB approximation, and that approximation is going to be that a of x is slowly varying, in which case the second derivative of a of x is equal to what? Tell me.
0?
Yeah, exactly. Good. You're getting the hang of it. Okay, so then that means that we're going to knock exactly is equal to what? Tell me.
0?
Yeah, exactly. Good. You're getting the hang of it. Okay, so then that means that we're going to knock off. So this part of the equation gets knocked off. Okay, so now
slowly varying. So the second derivative is 0. So if it's slowly varying. let's say we have this slowly varying. So we take the derivative, boom. And then we take the second derivative, which is just going to be 0. Okay.
Now the equation is much easier. So now equation 1 becomes really simple because it's just going to be, where did it go? It's up there. Yeah. Okay. So now it just becomes minus a of x ds dx squared plus k squared a of x equals 0. And now look at this. I can just cancel out the a of x. So simple. And it just becomes, then it becomes ds dx squared is equal to k squared. Oh my God, so simple. And so then it just becomes ds dx is equal to plus or minus k. All right. So we got that. That's nice. We got ds dx. But then we also see, but remember k, k is a function. So k is square root of 2m minus b of x over h bar is a function. And so then we see that s of x is equal to what? What's s of x? Tell me, solve this equation. I'm underlining it right there. What's s of x? Solve that equation. How do you solve that equation?
It's the integral plus or minus the integral of k.
Exactly.
Yeah.
That's exactly right. 0 to x, a of x prime. Oh, it's starting to look familiar, right? Remember? I was showing you before. So so now we got it, because check it out. We up here we have ds dx equals plus or minus k. So ds dx equals plus or minus k from below. And we can plug into there to get a. Actually, I don't think I want to write this and confuse whoever's reading these notes. So now we have it because we have s star and we have a star and we see size is that. So let's put it all together. So so a of x. What did I say was here? Yeah, c a of x equals c over square root of ds dx. So that means it's equal to c over square root of k of x, yeah. And then we have s of x there, and so now we see that psi is equal to a of x equals times e to the I s of x is equal to it's going to be equal to a constant over square root of k of x. That's a, but I can have two different signs of my s of x. So there's going to be 2 plus or minus I integral 0 to x k of x prime dx prime. Okay, and now because there's two solutions, a plus and a minus solution, that means each of them can get a different constant, c plus or c minus. And that is my WKB solution, psi e of x WKB. That is the WKB solution. And so that's kind of the same thing we would get with the little wheel, right? We got the little rolling wheel. So I just want you to see it's just basically the accumulated phase. This is just accumulated phase. Okay, so but now by doing all that math, we got a little bit of extra stuff. We see that there's a factor of 1 over square root of k of x. So doing the fancy math guy gave us a little bit more accurate thing. Okay, that is the WKB solution. And so now let's solve some problems. Now let's use it.
Can I ask a quick question?
Of course.
You know how you said slowly varying made a double prime of x 0? Can you kind of explain how you were able to know that was 0 using the slowly varying thing?
Well, yeah, it's kind of like, I mean, it's sort of like it's like, I mean, here's the thing. It's sort of like, that if I have, let's see, if this is x, and if f of x is some slowly varying function, then the derivative, well, I guess let's do it like this. Suppose, I mean, if f of x, if f of x is some very slowly varying function like this, then you can see that the derivative is just barely changing because it's not varying very much. And if the derivative is barely changing, then that means that the second derivative is barely changing. That's basically the reasoning. It's not like super precise, but that's the idea. Does that make sense?
Yeah, I could roll with that. Yeah.
I mean, there's other ways to think about it. I mean, there's a really nice derivation to describe the regime of validity of WKB, but I think I don't want to do that. I might do that. Do you come on Friday, or are you one of the people who don't come on Friday?
Yeah, I don't usually come.
Oh, okay. Because if you ask me on Friday, then there's another very nice derivation that shows the regime of validity in terms of energy and momentum and all this stuff, but it takes a little bit of time to go through it. I didn't want to do that today. So what I want to do today is I want to use it. I want to use the solution. Okay, so now let's use the WKB solution. And so there's two famous problems, two famous examples. One of them is bound states, and the other one is tunneling. And the tunneling one is even more famous. You get 3 stars, and this gets 2 stars. Okay, so applying WKB to find bound states and to do tunneling is the two famous examples. So let's do those. That's what I wanted to do today with these two famous examples. And so let's do bound states first. WKB can be useful for finding bound state energies. And so here's
what?
Suppose V of x.
Sorry, I just thought it'd be very funny.
A bumpy bottom well.
Okay.
So here it is. Let's draw a picture of it. So suppose it looks like this. It has some bumpy bottom, some weird potential. Okay, that's 0. And I'll just call
Okay.
this
Anyway. Okay.
It
was really stupid.
So I just drew. So that's just some bizarre well that I just drew out of nowhere. Okay.
Yeah.
And so now what I'm going to ask you is this: what is the energy of the bound states? All right. And so you've done this before. I mean, if it was a square well, you solve the difference equation, you match the boundary conditions, right? But now I give you this completely weird v of x, very complex. And this v of x is so complex that you have no idea how to solve the Schrodinger equation for this v of x. I mean, it's impossible, except for using a computer. You can numerically differentiate.
You know what I should do? I should build like a... This would kill me. I should build like a head box thing that I could put on, and then I could just scream into it, and then it'll just stop noise from leaking out. I should do that.
You can
But then I would have to have the mic very close to me, actually, so it'd suck. So I just build a soundproof area around me, a cube.
numerically solve this problem via numerical techniques, but solving it analytically is, there's no way you can do it. So you're sitting there going, well, how am I going to do this? And suppose that you don't have a computer to numerically solve the Schrodinger equation. So instead, what you do is you just say, let's use WKB. And with WKB, it becomes really pretty relatively easy. Still not completely trivial, but like 1,000 times easier. So what we do is we use the WKB solutions. And I say solutions because remember there's the plus minus. There's the plus and minus cases, so there's like those two solutions. So here's the WKB solution of the Schrodinger equation. WKB says don't numerically differentiate the Schrodinger equation. You don't need to do that. Instead, just make the assumption that the slowly varying thing is okay. And if that's true, then you can write down the WKB solution. You can say that the wave function inside of that bumpy well is equal to the positive one, a over square root of k of x times e to the plus I 0 to x k of x prime dx prime, and then plus the negative solution, b over square root of k of x e to the negative I 0 to x k of x prime dx prime. Okay, you see that? So I'm just saying that that's the WKB solution that we derived, right? Here it is. We derived it using all that fancy math, and there it is, and now I'm using it. So I'm just saying I have these two components of the WKB solution, the plus one and the minus one. I add them together in some arbitrary way, and that's got to be my wave function. That's the whole point of WKB. So you say, good, there it is. That's my wave function. And so now what do we do next? What do you think we're going to do to get the bound state energies?
Solve for the coefficients.
We got the wave function. So this is the hard part. This is like solving the differential equation. But now what do we do next to get the energies? Can you tell me? It's what you've done before when you solved a similar problem.
Solve A and B.
Well, it's a second order differential equation, so there were two solutions. We got them. There they are. And now that we got them, what do we do with them? How do we move forward? What's the next thing? Get the solutions of the equation, then what do you do? Well, if I gave you this problem, and I said, what are the solutions? You would solve the Schrodinger equation that says psi of x is equal to a sine kx plus b cosine kx. That's what you would get by solving the Schrodinger equation. And to get those energies, what would you do next? What would you do next? Yeah, you've done it a million times.
Wouldn't you plug in the boundary conditions?
Yeah, right. That's what you do. You plug in the boundary conditions. That's exactly right. So next comes boundary conditions.
Oh.
And so that's what we do with the WKB.
Yeah, boundary conditions to get A and B. Yes.
Solve the differential equation. And that's what the WKB gives you. It gives you the differential equation solution. But then you still got to do the boundary conditions. So next we have to do the boundary conditions. But here's the thing. To do the boundary conditions for a bound state, then to do the boundary conditions for a bound solution, it tends to be simpler not to use the complex exponent, but instead the complex exponent, what do we use instead? And it's right there staring at you on the page. So I want to convert the WKB solution to what? Can you guess?
Cosines?
Exactly. So bound state problems, and you know this from last semester, are always easier when you use trig functions, easier with sine, cosine. But if you have traveling wave solutions are always easier with the e to the ikx, right? The plane waves. You guys remember that from last semester. So this psi e of x, so we'll convert it to another form, which you know that they're equivalent. It's 1 over square root of k of x to this. We'll do this a sine of 0 to x k of x prime dx prime plus b cosine integral from 0 to x k of x prime dx prime. Okay, so I'm just going from one form, just a simple transformation for convenience. And so now we plug this into the boundary conditions. So this is easier. And so let's plug it into the boundary conditions. And so let's do the first boundary condition is that the wave function at x equals 0 is equal to what?
0?
Yes. And so what does that say about the a and the b?
B equals 0?
Exactly. You got to have b equals 0 because that cosine messes you up. So this thing can't be 0 at 0 unless b equals 0. That's right. Good. And so now the second one is going to be psi at x equals a equals what?
0.
Exactly. It's 0. And so now at x equals a, it's going to be 1 over square root of k of a times sine of integral 0 to what? What's the top of my integral? A. Right. Because the phase winds from 0 to a. So the little wheel is rolling along. And the phase is k of x prime, d of x prime.
dx prime.
The b is gone. And so this whole thing is 0. But this whole thing can only be 0 when integral of 0 to a k of x prime dx prime equals what?
0 or 2 pi?
Is it 10 pi?
That's right.
Yeah.
That's right. And so that's the constraint that you just derived. And so what you just derived is that the integral from 0 to a of k, which is square root of 2m e minus v of x over h bar dx prime equals n pi. And so this is a constraint this is a constraint on what variable. When you look at this thing, what's the only variable in here? Tell me.
The energy.
Yeah, exactly. So that's going to be, we'll call that E sub n, because you're going to get a different E for every different n. You see, they're connected. And so this is how you find. So you solve this. The E sub n. So this is giving you.
That's how you react when you.
Reducing it.
Can you imagine if you're in like a class and there's a guy who, when something clicks for him, instead of going he just goes. So I was like, oh, why is it that when we assume a slowly varying potential that we can approximate the second derivative to go to 0? Oh, that's because with a slowly varying potential, basically, if you have your derivative, the slope is barely even changing, so your derivative becomes basically a straight line. So the derivative of a straight line is equal to 0. Oh, that's really funny. Okay, anyway. So your energy is quantized.
It still might be hard, because you might have to still do some numerical work to even solve this integral. But solving integrals is easy, comparatively easy. Solving integrals is much easier than solving differential equations. Okay, so what I want you to also see is that physically, this is basically just doing something that you guys have done before. It's just physically, what we're doing is we're just fitting an integral number of half wavelengths into the well. That's all this is. It's just fitting waves into the well. I want you to see that. We're just the wavelength is changing of the waves as you go through the well, but what this formula is doing is just saying even though the wavelength is changing, you have to have an integral number of half wavelengths in your well. That's all that this equation is saying. So it's a sort of a very famous and sort of intuitive kind of result. Okay, and so this is what we get from WKB. So this is a very beautiful and simple result. So, but and you could do it. You could do it like for a square. Like if you had suppose I have V equals 0 from 0 to A. You're a situation that you know this one. So then what we see is we have 0 to A, square root of 2me n over h bar dx prime is equal to n pi, and then we're going to get square root of 2me n over h bar times a equals n pi, and then you can solve that to get E sub n is equal to n squared pi squared h bar squared over 2m a squared.
Wow.
So this is the infinite square well, square well. So this is our favorite quantum mechanics problem. So you can see that
it works.
I'm just seeing how the infinite square well fits into this formalism. But the point of this formalism is that it works for much more complex potentials than the infinite square well. So I want you to see that. But I'm not going to do any more examples of that. Okay, so now what we're going to do, so that's all I want to say about bound states. Now let's do tunneling. And this is actually the more famous problem. This is actually the more important one. WKB is more importantly used in tunneling. And so what we want to do is we want to apply WKB to tunneling. So here's the situation. Suppose you're given this. Suppose you're given this very weird potential well, where this has some very confusing V of x form, but then we have the energy is here. So suppose I shoot in a particle with that much energy at this well, and I want to know what's the probability to get through. The probability of transmission. That's my question. Okay, that's a very important question. What's the probability of transmission? Now you guys have done this before, and so you already know, if you already kind of know what to do. If this region here is x1 and this region here is x2, then you know that I can label this region 1, and this region 2, and this region 3, and you know the form of the wave function. You know that in region 1, I have my incident wave function, looks like that, and I have my reflected wave function, like that. And what's the form? The incident wave function, what does it look like? What's the form of it?
E to the ikx.
That's right. And what's the form of the reflected wave function?
E to the minus ikx.
Yes.
R times e to the minus I. Yes. Yeah, exactly. And then here, then on this side, I have a wave function which is going in what direction on the right-hand side?
In the plus direction.
Yeah. And that form is going to be, what is it?
Is it t e to the ikx?
Exactly. That's exactly right. But here, now in this region though, it's confusing because normally you would have your exponentially dying solution and your exponentially growing solution, remember, from last semester? And then you would just match everything at the boundaries for the flat top, because you can solve the flat top, and you did that last semester. But now I didn't give you a nice flat top, I gave you a bumpy top. And so the bumpy top is so complex that you have no idea what to do. You have your exponentially, that's exactly right. But here, now in this region though, it's confusing because normally you would have your exponentially dying solution and your exponentially growing solution, remember, from last semester? And then you would just match everything at the boundaries for the flat top, because you can solve the flat top, and you did that last semester. But now I didn't give you a nice flat top, I gave you a bumpy top. And so the bumpy top is so complex that you have no idea what to do. You have no idea what's going on inside. So what do you think we're going to do on the inside? Because to solve this equation, we need to solve the differential equation, and then after you solve the differential equation, that's when you then match boundary conditions. The problem though, when you have a bumpy potential, is that you can't solve the differential equation, you don't know the solution. So what solution are we going to use on the inside? Tell me.
can we still use the same solution, but the
What
kappa is
solution?
going,
What solution?
the e to the, I guess it was kappa x.
Well, those kappas were constants in the past.
Can we do that phase thingy that we were talking about instead on those?
Exactly. And that phase thingy is called what?
The WKB approximation?
Exactly. We call it what it's called. It's called WKB. That's right. We'll just use a very trivial phase approximation trick. And that's a trick for solving the differential equation. And that's what we'll do. It's not really the true solution, but it's an approximation to that solution. And that approximation is the WKB solution. So we'll use that. That's right. That's what we'll do. Okay, so let's do it. And then we'll match the boundary condition. So let's do all that. And then the whole point is to find T, the probability of transmission, the transmission coefficient. Okay, so let's do it. So let's write it all down. So let's write out all the equations. So psi in region 1, psi of x. And I'm going to do it, this is how I'm going to do it in region 1. I'm going to call this, in the left-hand part, I'm going to call that solution e to the I k1x plus b e to the minus I k1x. Okay, where k1 is equal to square root of 2me over h bar. So does that make sense? So that's just the incident wave plus the reflected wave, where I use a and b instead of 1 and r. But it's okay, it's the same thing.
Yes.
And now in region 3 of x, I'm going to use this f as in Frank e to the I kx. That's the transmitted wave. Where k, where I have the same, that's the same. Actually, let's not call this k1. Let's just call it k. So we don't need that one. Okay. So, and in the region 3, I have just f as in Frank equals e to the I kx. That's the transmitted wave.
Can I ask a quick question?
Yeah.
Would the transmitted wave after having tunneled have a different k to kind of, because like I would assume like in between the energy is not the same, and to have like a continuity, it would have to like not have the same k as before?
No, that's not right, because the thing is that, remember, the wave function has a well-defined energy. And the energy is the same in all regions of space. And so the same energy on the left is the same as the energy on the right. That's really important. Did you see that? You see on the left, I'm going to do this. You see this thing right here? I'm drawing this vertical arrow. See that?
Yeah.
That is E minus V. And what is E minus V? Kinetic energy. That's the kinetic energy. So the kinetic energy on the left is E minus V. And now let's look on the right.
Oh, I think I'm confusing the energy with like probability or something like that.
Yeah.
Because it would have the same energy, but like the probability of finding it changes definitely, but not the
Oh yeah, the probability changes all over the place, right? The probability goes crazy, but the energy is the same. But that's why I really want to make that clear. The kinetic energy is the same on the right and the left, and so the wiggliness, which is the K, is the same. But in the middle, it gets all crazy. Okay, so we're doing the easy parts now, but the middle part is hard. So let's do the middle, psi 2 of x. And so now we need the WKB solutions. But now the WKB solutions are going to be a little tricky now. Let's go back to them. Where the heck is it? Yeah, so here's the WKB solution. See, I did it up here. You see it's here. Right, I'm going to put a little star there. See that little star I just drew? Circle around it. So that's the WKB solutions. But notice that K is the square root. Where's K? Oh my God, K. Where are you? There it is. Okay, here's K, where this little star is. K is the square root of E minus V of x. So K, now because I'm underneath the well, K becomes complex. So now the WKB solution will look a little different. It's going to look like, it's going to be C over square root of, we call it kappa of x times e to the minus integral x1 to x kappa of x prime dx prime plus d over square root of kappa of x e to the plus x1 to x kappa of x prime dx prime. See, that's the form of the solution inside of the region 2, and that's exactly the WKB solution. But now it's not an exponent. It's not a complex exponent. It's a real exponent, right? Because of the nature of complex numbers. And notice that the starting point is well defined, x1, because it starts at x1 and then this phase winds to the location x. But now the phase is different. Now I basically have an imaginary phase, but that's okay. It's just complex numbers. You can handle it. Okay, so this is the form of the WKB solution. And so now now what we have to do is find, and notice that the starting point is well defined, x1, because it starts at x1 and then this phase winds to the location x. But now the phase is different. Now I basically have an imaginary phase, but that's okay. It's just complex numbers. You can handle it. Okay, so this is the form of the WKB solution. And so now now what we have to do is find the transmission coefficient, T. And do you know what T is? Can you guess what T is in terms of these all these stuff that I just defined? What is it that we're trying to find?
Probability of starting at 1
Probability
and
of
into
passing
3.
through.
That's right. But in terms of all of these coefficients, A and a B, C, D, and F, what is T in terms of all those guys? In terms of A, B, C, D, E, F, what is it?
F magnitude of F squared divided by the magnitude of A squared.
That's exactly right. That's what we got to do. That's what we got to do now. And how are we going to find T? What are we going to do to find T? Same thing you did last semester. What are we going to do? By doing what? We have, yeah?
The boundary conditions?
Exactly. Because this is the solution to these are the solutions to the differential equation. And once you have the solutions to the
Right,
differential,
so the reason why is because F is it passing through, A is the amplitude of it not passing through, and so you're taking the probability, which is just going to be the absolute value squared.
equation, the next thing you do is you always do the boundary.
Okay.
So let's use the boundary conditions. So but to do the boundary conditions, we're going to do some tricks. The tricks that we're going to do is we're going to assume large energy and not much reflection. And that is in keeping with the philosophy of WKB, that the energy of the particle is very high. And if the energy is high, there's not much reflection. So what we're going to do is we're going to assume, we're going to we're going to take out the parts that are due to reflection. Because look, in the solution number 1, what part is due to reflection? In solution number 1.
The b e to the negative ikx.
Exactly. So we're going to assume that b goes to 0. Now in solution number 2, what part is due to reflection? This is less obvious. Let's just take a look at region 2. In region 2, it's like I'm inside of the well, right? And if you guys remember how you have the exponentially dying solution and you have the exponentially growing solution, right? For the flat well, you remember that from last semester, right? And so the way to think about this is that this dying part is because as you move forward in the classically forbidden region, you go dying, you go down. But then you can hit that wall and reflect, and then you die double death, because once you reflect against that wall, you die some more. So if you go, you're dying, and then if you bounce and accumulate more complex phase, you die some more. And so this solution, which I'm giving a star, 2 stars, that solution is due to the reflection. That's how you should think of it. That's the exponentially, because remember how you always had the exponentially dying solution, exponentially growing inside under your well? And remember how you were always confused, why is there an exponentially growing solution? It kind of didn't make sense, but you just went with it, right? Well, the exponentially growing solution is really the reflected solution. It's the accumulated phase from the particle bouncing and dying some more as it comes back. So now back to the WKB solution, which of these 2 solutions is due to reflection? The C or the D?
D.
D.
That's right.
Yeah,
That's the
because it's
reflected one.
plus.
Reflected solution.
Wait,
And
what?
so we're going to ask 2 solutions is due to reflection. The C or the D?
D.
That's right.
Why is it D?
That's the reflected one.
Why?
Reflected solution. And so we're going to assume that D goes to what? Tell me.
0?
Because we're killing reflections. And so that means D must be what?
0.
0.
That's right. Okay, and that makes everything a lot easier. So now let's match the wave functions at x1 and x2. Okay, and so what I have at x1, I have psi 1. See, this is x1. Let's remind you. See, here's x1 and here's x2. Okay, so those are the boundaries between region 1 and region 2. So I have psi 1 at x1 is equal to psi 2 at x1, right? And so that then gives me this incident wave e to the I k x1 is equal to the. Now I got to do this one. I got to do this guy right here. And so it's going to be c over square root of kappa of x1 times e to the negative integral from x1 to x1 of kappa of x prime dx prime. So what does this integral equal? What is the integral from x1 to x1?
0.
Right. That's right. And so that's equal to c over square root of kappa of x1 times e to the 0 times 1. So that then tells me then that I have, so that's pretty useful. So that tells me then that a is equal to c over e, let's do this way. It's c over square root of kappa of x1 e to the negative I k x1. Okay, so we got a. That's pretty cool. But we need to get f, so let's do x2. And so from x2, we're going to do psi 2 at x2 is equal to psi 2, or psi 3, I mean, at x2. And so that's going to give me then c over square root of kappa x2. But now the exponent is going to be e to the negative, right? Because I'm still using this WKB. It's x1 to x. But now it's x. But now it's going to be x1 to x2 of kappa of x prime dx prime, and that is going to equal the solution on the right hand side, which is f e to the I k x2. Does that make sense? And so then that tells us then now we can solve for f, and we see that f is equal to c over square root of kappa at x2 times e to the minus I k x2. We got f. So we got a. We got f. What are we going to do now to get t? T is equal to what? What do we do now?
Divide?
Yeah, it's just f over a magnitude squared. So let's do that. So let's just divide those 2 things. So it's going to be magnitude squared. I'm going to put the f on top, and that's going to be c e to the minus I k x2 e to the negative x1 to x2 kappa of x prime dx prime square root of, oh, and then let's get rid of that. And then I have my divided by square root of kappa at x2. Okay, but now I got to divide that by a, and so for a on the bottom, I'm going to have e to the negative I k x1 times square root, oops, and then the square root is going to be on top because I'm dividing it. So on top it's going to be square root of kappa x1 magnitude squared. Okay, now there's a couple things to notice here. First, I want you to look at square root of kappa x1 over square root of kappa x2, and that now kappa. What the heck is kappa? Do we define kappa? I'm sorry, I didn't even write down what kappa is. I mean, kappa is going to be equal to square root of 2m v of x minus e, because it's an underneath potential, and that's kappa. But what is kappa at x1 and x2? So kappa at x1 is equal to the square root of 2m e minus v of x1. Oops.
V.
V of x1 minus e. But what is the definition of the turning point, or this point where these cross? See at x1, the energy hits right here. So what special thing is, what is the relationship between the V and the E at x1 and x2? The potential and the energy at x1 and x2. What can we say about them? We're almost done. I just want to finish this last little bit.
They are equal at the turning points.
Yes, these are the turning points. Turning points. E equals V. And so what does that mean then? What do the kappas equal? What do they equal? I got this minus this. V and E are equal. And so what is kappa equal?
0.
That's right. And so this thing is a 0 over 0. Now, this is actually slightly tricky if you want to like delve into all the mathematical nuances of it. But you know me, I don't want to do that. I'm not
So it's just
I'm
0.
not so excited about all those mathematical nuances. I'm just going to do the cheap and simple thing, which is to say that 0 over 0 is equal to what? Tell me.
0.
1.
1.
Yes.
Oh, to 1?
But I will tell you that I am sweeping stuff under the rug. There is some trickery, there is some complexity that happens at the turning points in the WKB approximation. But I have been using WKB for 30 years, and I have never had to worry about that trickery in 30 years. So I'm just going to ignore it because it sort of doesn't. It's never been important to me. 0 over 0 is equal to what? Tell me.
1.
1.
Yes. But I will tell you that I am sweeping stuff under the rug. There is some trickery, there is some complexity that happens at the turning points in the WKB approximation. But I have been using WKB for 30 years, and I have never had to worry about that trickery in 30 years. So I'm just going to ignore it because it sort of doesn't. It's never been important to me. So you see that these two guys are going to cancel. And when I do the amplitude squared, then these two guys are going to turn into what? What's going to happen to these two factors?
They go to 1.
They're going to go to 1. That's exactly right. And so in the end, we get this. We get that T. Oh, and something else. There was another C down here. I'm sorry. Because F has a C in it and A has a C in it. So there's a C on the top and the bottom. So the C's cancel. And you get that the transmission coefficient is equal to, basically, there's a C on the top. Oh, and something else. There was another C down here. I'm sorry. Because F has a C in it and A has a C in it. So there's a C on the top and the bottom. So the C's cancel. And you get that the transmission coefficient is equal to basically just this integral squared. And so that means it's going to be e to the negative 2 integral from x1 to x2 kappa of x prime dx prime, where kappa of x is equal to square root of 2m v of x minus e over h bar. And that is a very famous relationship. That is the famous WKB relationship for tunneling. The transmission the WKB tunneling transmission coefficient is very famous, and it's very useful because it's very simple. That's the result that we just derived. And it's just so simple and beautiful. It's just if I have a potential and I want the probability to tunnel through it, I just have to integrate, do this little simple integral. That's all I do. And so that's what, you just have to do now the integral under that potential. Okay, so that's a good place to end. I'm sorry for going over. Bye-bye.
Thank you.
Okay, bye-bye.
Thanks.
Okay. Okay. Sure. All right, that's that. I think that's pretty much it. I gotta use the bathroom. And then I have to update my finances on Google Sheets. And then what? I think that's it for today, probably. But yeah, all right. I'm a peace out now. Peace out. Peace out, players. Keep studying. Keep your grind on. Keep your grind on. Keep your hustle hard. All right? Don't forget. The money don't come without work, okay? Under this economic framework, we are paid only for the amount of hustle that we put in. So we get our paper, we stack paper up by grinding up. Paper is proportional to grind. So if your grind is up, your paper goes up. All right, guys? Never forget that. And with that, I'm out of here. Salut. Salut is hello in French. Salute. Bon voyage. What is bye again? What is bye in French? Hold on. I have to think about this. There's salut, which is hello. What is bye? What is it? I don't want to... Bonsoir is not it. That's good night. Bye in French. Au revoir. Salute, and au revoir.